welcome to chapter 12, DC electric motors. This is only a really short chapter, but there's a little bit of explaining in it, and it is spinning. Now, the electric motors that we're going to talk about here are dumbed down beyond belief, okay? They are just incredibly, really simple examples of what an electric motor is. To the point where if you were to actually rip open an actual DC electric motor and look at it, you would think to yourself, how in the hell is this anything like what, my teacher has explained to me? It looks nothing like the diagrams, but that's because what you're doing right now is you're learning the idea of how an electric motor works. You're not actually learning how to build an electric motor. There's a ton of really clever engineering that goes into making a real electric motor. What you're learning here is the idea of how they work, the principles in which they work, meaning that one day you may take off and become an engineer or a scientist and contribute in some way. Okay, as usual, I have created a help sheet for you. This help sheet is pretty much all typed out though, no drawings by me or handwriting. You can see that this help sheet has a couple of things in it that are not used in this chapter, okay? Basically, any reference to generators, as you can see here, okay, any reference to a generator actually belongs in the next chapter. Okay, it's all part of the same area of study, but you're not going to focus on this aspect of it yet. So you won't need any of that, okay? Everything in this chapter is really related to the operation of an electric motor. Everything's electric motors, all right? Now, you can see there's a lot, this is very text heavy here. Over here, there's a lot of writing. In this writing here, in these blocks of writing, what you've actually got are the culmination of years of teaching this and looking at exams and completing exam questions where the focus is the explain aspect of the exam question. So what that means is that a lot of this writing is what you would be your go-to on your help sheet in an exam or in a SAC. Okay, this is where you would go to write down, explain the role of a split ring commutator in a DC motor. Okay, so then you would go down to where it says split ring commutator. So that says slip ring, so that's not it. Come over here, it says in the electric motor, the split ring commutator, or often referred to just as commutator, its role is all of this. And so you would adapt this answer into your solution to your answer for your exam or SAT. Okay, and making sure that, of course, you try to reference the question in some way, because, as I've mentioned before, examiners don't want to see just regurgitated standard answers thrown down on exam questions. They want to see that you've actually thought about the question that they've asked. Okay, so you can see here there's all the stuff that you're going to need. This is all, of course, going to be available on OneNote, in Compass. I will leave it as a Word document on Compass so that you can manipulate it, change it, copy, paste, do whatever you like to it. Okay? Chapter 12, 13 and 14 go into this area of study. Okay? Anyway, so let's get to the notes and then have a look at a few questions. Okay? Now, basically, we've already covered taking a length of wire, running a current through it, and immersing it in an external magnetic field. When you immerse it into an external magnetic field, the electrons running through that wire are going to individually experience a force on them. That force is the direction of that force you can figure out using the right-hand rule. Okay? So, the right-hand rule is, the reason that we teach the right-hand rule is because it gives you a whole lot of applications that you can use it on, and electric motors is one of them. Here they have a diagram where the right-hand rule is being demonstrated. You have a length of wire running through here with a positive to negative terminal connection. The wire is immersed in the field in between the two poles of this magnet, and the right hand rule says, okay, positive to negative, and we're going to go current in this direction. The field runs from north to south. There are little arrows there that if you look at your own notes, you can see them more clearly than on this screen. I'll zoom in a bit if you like, just make it a bit easier. And as you can see, the force is now, when you line everything up, the force is directly up, okay? So, that's nothing new, right? In the operation of a motor, alright? Now, I have a little model to show you as well, but let me just introduce the idea with this diagram. As you can see, there is a loop of wire immersed inside an external magnetic field. So this would lend itself perfectly to the right-hand rule, okay? There will be forces acting on this loop of wire if a current is running through that loop. Now you can see in this diagram that the arrows give you the direction of the current through the wire. So that's pretty easy to understand there's an arrow. So I often, if these arrows aren't drawn in to a question that I'm trying to do, you'll see when I show you my annotated solutions, I always put the arrows in. That way I don't get confused. Alright? So, arrow goes in. You can see it will move through this loop in this direction as shown in the diagram. Okay? And then back out again. So obviously there's the positive terminal here and the negative terminal there. Often they'll just leave it connected to a battery. And don't forget that if this is the diagram of your battery, the long line represents the positive terminal. And it doesn't matter how it's drawn. It can be drawn as a set of cells all lined up. The long side, the side with the long length, that's the positive. So you always just jam a big plus right next to it. You don't even need to do the negative in the other one because, you know, who's got time for that, right? So there's a wire coming through here to some sort of light glow. You know that the current is moving in this direction. Okay, conventional current, again, don't forget that's really important. Anyway, now, you can see that the current is running through here in this direction. Now the best way to give yourself, because often the question is about which way will the wire try to spin, okay, or attempt to spin. Now, the best way you can do this is you look at the external magnetic field that you can see running between the poles, the north and south pole, and then look at the direction of current, but don't try and look at the whole loop, okay? If you're looking at the whole loop, it becomes super confusing, especially when you start to imagine it moving, all right? Once it starts moving in your head as you're trying to imagine what's going on, then it's super confusing, all right? So what I do to try and alleviate the confusion is I focus on one arm, the arm that is running perpendicular to the field, okay? Perpendicular to the field is kind of important. All right, so I don't trust myself to draw a straight line there, so I'm going to, let's use my ruler. Lovely. So I'm going to focus on that arm of the loop. And I'm going to ask myself, what happens to this arm of that loop when there's a current running through it and it is immersed in this external magnetic field? Whip out my right-hand rule and line it up. If it lines up in a logical way, as per the rule, then you know that there is a force acting, okay? If you can't make it line up, well then it implies that there is no force, and we'll talk about that in a second. Over here, I'm going to line up my thumb in the direction of the current. My fingers are running in the direction of the field, north to south. The force is up on this side of the loop, which means I can draw a nice little arrow going straight up. So the force on this side of the loop is up, okay? This is where it can get a teeny bit confusing. Imagine this current, right, coming in from the positive terminal, making its way down this side of the loop, all right? Line it up there. See if you can make your right-hand rule work on that side of the loop, okay? What force is that side of the loop experiencing? Well, because you can see that on this side, the current's moving towards you, but on this side, the current's moving away from you. So, does that make a difference? Of course it does. So, line it up. My thumb runs in the direction. Now I'm looking at this length here, from here to here. It is perpendicular to the field, which kind of helps. My thumb moves in the direction of the current. My fingers are running in the direction of the field. And which way is the force? Oh, look at that. Down, okay? So on this armature, this part of the armature, okay, on this part here that's obscured by the pole here of the magnet, you have a force acting down. Now imagine, what would that result in? Well, let's see. If I push one side of the loop up and the other side down, I'm going to get a twist. Here's one I prepared earlier. This is in the same orientation, same orientation as the one on the board. You can see there is a loop that moves. All right. Okay, here it's all made out of wood, it's not real, don't let it fool you. Okay, this amazing construction here. There are a couple of wires here, which just imply that's where the current would come from. You've got your spinning loop, all right? In this orientation, you've got these blocks of wood represent the poles, the two different magnets, okay? One with its north end pointing in this way, and the other one with the south end pointing in this way, meaning that there's a field running north to south from white to brown there, as you can see. Okay, now if I try and make this as a sort of physical representation of what I've just said there, if I push up on one side and down on the other, you can see, look what happens. Oh, look at that, it spins. How cool is that? All right. And everyone, you know, back in the days, like, oh wow, we can make motors, this is great. Finally, we'll be able to vacuum our rugs, right? Anyway, now, the problem is though, what happens when the loop goes vertical and then tries to get all the way over to continue the spin? Because everyone needs a motor that does this. Nobody needs a motor that does this. Okay? And I'm implying, obviously, that this might happen, okay? So why? Why would that happen? Excellent question. Let's say this arm here, which is connected to the negative terminal, is now being forced up by its reaction to the external field. It's being forced up, so now it's twisting and it's going up, all right? Probably better to look at it like this. So it's being pushed up here. Now, imagine the current is moving down this line and is connected to this wire here, okay? So the current's coming in and say it's moving down, all right? Now, if it's moving down, then there'll be a force on this particular, in this version, it'll be a force down, if I use my right hand rule, okay? So it'll be a force down, okay, if the current's going towards you. When it gets down to here, the current is still moving down, okay? Now, if I try and rotate it over to this side, what actually happens to the force on that side, on this side of the loop, which was back over here a second ago? Remember, current moving down towards you, the viewer, okay? As it comes around here, the current's still moving down towards you because it's still connected to the same terminal. What does that mean? Well, let's line up the right-hand rule and find out, shall we? So, that's still the North Pole, okay? Remember, it was pushed down to get over here. Now, to get over here, once it gets over here, the current's still moving out towards you. The field is still as it was. So, which way is the force now? My thumb is running towards you because that's the direction of the current. The field is this way, okay? Sorry, current's moving towards you this way, all right? Why would I point? I pointed the other way. Anyway. The current is still running towards you in that arm that we're focusing on, and the field is still in the same direction that it was. So which way's the force on that armature? Down again. So it's down here. Flick it over here, still towards you, feel that way, down here. Right hand rule, still pushing down. Flick it over here, the current's still going towards you, which means the field hasn't changed either, and therefore down again. So what are you getting? You're getting a wobble. don't need that. That doesn't actually help, all right? That doesn't help at all. So someone had to come along and come up with a clever little trick to try and get this from wobbling to spinning, all right? Now, I've used the word already a couple of times, and basically what we're doing here is we're going to look at what a split ring commutator is. So what does the split ring commutator do? That's the little bit of cleverness that was invented to allow a loop to spin continuously. Basically, what it does is it changes, its operation is to change the direction of the current through the loop every half turn. That way, the current through the loop lines up appropriately with the external magnetic field in a way that keeps pushing it in the same direction. Now let that sink in for a second. That is something that you really have to be able to imagine because it makes doing all this sort of stuff much easier. Now in this cool little model, you can see that what we've got is a bottle cap which represents the commutator. And if you can see it closely enough, you can see that there's a black line drawn at the top, and when I rotate it, and at the bottom. That black line represents a break. Okay, so the basically what you've got here is, if you look at your help sheet, this is a version of a split ring commutator. So it is a metal ring that has a break in it here and here. All right. What that means is that if this is connected to one terminal of the loop, and that is connected to the other terminal of the loop, and then each one of these rings is connected with what is known as a brush that is connected to a power supply, then if we send current from a positive terminal through here, the current moves through this wire into the brush, which is a metal object, through this loop, all the way around, and back out here to the negative terminal. Now, what happens is that if we look end on, that this little wire here is not actually physically connected to that terminal. It is basically a piece of wire. If this represents the half of the ring of the commutator, then this here, okay, is the wire. This is the end. This is the end of this wire here. That's a finger, right? So if you imagine it, it just touches, it glides along, okay? So while it's touching this metal part here, this half of the commutator, the ring, it's making a connection to a particular battery. So my arm represents the connection over to the battery, to the terminal, okay? So the current's running through here, and as long as this wire is touching, it's live, okay? But when it gets to, so if I show you that end of the wire is, say, here, okay? And as the loop turns, because it's immersed in this field, a couple of magnets out here, as it turns, this is going to move, sliding along, until it gets to the top. Okay, so when this wire orientates itself vertically, what happens is it loses connection. It loses connection with both terminals for an instant, okay? Because that's where the holes line up with the connectors. These are the brushes here, okay? All right, so when it goes vertical, it's not connected to either, all right? Now, when it gets from this ring, moves over here, up to here, like I just said, you've got no connection. So this is no longer live, all right? Now, as it continues, now basically the way it's explained is it continues with its momentum, all right? So the loop has been moving at some velocity. Its momentum carries it over the gap, all right? So this little bar here, this end of the armature, now flicks over and moves from connecting to this ring to connecting to this ring. Now notice that this ring is actually connected to the negative terminal. So when this loop, when this arm here travels all the way around, okay, travels all the way around, and it connects to the other terminal, well now this arm is over here. Oh, sorry. This arm is over here, and what it means is now it's connected, rather than having the current moving up it in that direction like it was when it was on this side, now it's moving in this direction. Okay? So rather than moving away from you, when it connects to the other terminal, it's now moving towards you. And what is all that for? What does it mean? Why do you care? Because when it connects to the other side, it means that the force continues to push the loop in its little circle, in its spin, rather than have it, as I demonstrated earlier, flicking backward and forward, wobbling. Okay? By changing the direction of the current through the loop every half turn, it maintains the same spin all the way around. Okay? That is the point of the split ring commutator. Now, where it gets confusing is that there are two ways of connecting a motor. Now, all of this theory is about the DC electric motor. Why DC? Why not AC? Okay? With an AC electric motor, you wouldn't need commutators and all sorts of weird engineering. Okay? But for some reason, all electric motors are pretty much DC. So we take the AC current out of the wall, okay, out of the power supply, and we convert it to DC, and then we run it through a DC motor. Why? Well, there is a really good reason for it. Let's say you didn't connect your motor to a DC power supply and you didn't use a commutator. And let's say you used slip rings. Now here, this is a slip ring. Notice no brakes. Basically, it maintains a connection constantly. So if you were to look at a slip ring in operation, you'll notice in this diagram, one of the terminals of the wire, of the loop, touches this ring here. And the other one touches the other one. So this one does not connect to this brush, it only connects to this one. And basically, it's a ring and the wire moves around it continuously, always touching. All right? For that to work, remember, if you have a constant magnetic field, then you do need to change the direction of the current through the loop every half turn. Remember, that was the point of if you were supplying a DC current, you need to use a commutator, okay? If you don't want to use a commutator, well then you have to use, you're going to use slip rings, which just maintain a constant connection, so the direction of the current through the loop, if you were to connect it to a DC power supply, would never change, hence thus therefore, the loop would just wobble. How would you fix that? Well, you disconnect the DC power supply, and connect an AC power supply. What does AC current do? It changes direction on its own. So the current coming from the power supply already changes direction every half cycle. Remember, an AC signal looks like this. So it is changing direction every half turn, all right? Which means you don't need a commutator in this case, because it will spin. So why don't we do that? Okay, why don't we do that? Because you don't have a lot of control over a motor like that. Normal voltage coming out of the wall comes out at a frequency of about 50 hertz, 50 cycles per second, okay? So if you were going to rely on your electric motor taking its supply from from our normal power supply, then pretty much you're stuck with a motor that goes that fast, and that's it. You can't really do anything. You can't speed it up. You can't slow it down. It's 50 hertz. 50 hertz is 50 hertz. All right. So what we've done is we've taken the AC signal, converted it to DC, and then put it through a commutator. Now you can actually have speeds, because how do you increase the force on a loop? You can increase the current. Okay, so if you increase the current, you speed up the motor. Decrease the current, you slow down the motor. F equals nibble, remember? N-I-B-L, all right? So, by using DC power supply and a commutator, you gain really good control over your motor. And that's the point of using a DC motor. Otherwise, all motors would just be going the same speed, depending on what the frequency of the signal was. All right? So that's the reason for it. Okay, well, that's one of the reasons for it. It's the reason I know. You know, you do need to, you know, anything that I've explained to you, if you're looking at it, you think to yourself, well, you know, YouTube exists, right? So you can, at any time, go to YouTube and go, explain DC motors, DC motor operation, animation, you know, those kinds of little things, and you'll get lots of short little videos that will actually show you so that you can build a much stronger picture in your head of how these things work. That way, when you ask certain questions, because they only ask you a handful of really basic questions, and then they start to push you and say, oh, well, what if I do this and what if I do that? And it really helps you have a really good picture of how these things work. And the best way to really build that up is looking at lots of animations and even models, physical models and things like that. They really help. Okay, so let's move on. Now, the next idea is the direction of the force on the wire, okay? Again, we are going to focus on one piece of wire, okay? We're going to focus on this one here. Now, let's say that that is this top wire here, okay? Now, I'm going to orientate it this way so it's in the same direction as the diagram, and we're going to have a look at what the direction of the force on this length of wire actually is, okay? Because this is where we learn the difference between the direction of the force and the direction of torque. All right. So, for the direction of force, you've got the field running this way. Now, in this diagram, in that diagram, the current is moving in this direction. Okay. Let's see. Does that help us? Yeah, it does. Good. All right. So the current is moving towards you, all right, through this arm here, okay? Now, for that, what is the direction? In this orientation, what is the direction of the force? Well, it's moving towards you. So my thumb is going this way along this bar here. The field is north to south this way. So there's a force up, okay? Now, let's look at it in this sort of twisted, sort of elevated position. What is the direction of the force now? All right, so right-hand rule, north to south, current still going towards you. So can you see that if I line up the magnetic field lines with the current in the wire, the force is still directly up. That's what this diagram is telling you, okay? In this position, all right, the force is directly up. As the loop spins, if you take a minute to really look at how your hand changes and what difference this location here actually makes, you find it makes no difference. What happens is that the force on that wire is always the same and it's always up, okay? It's always up until you get to the top. All right? Now, technically at the top, if you're using a commutator, it loses connection and then the force goes to 0 for an instant. Okay? Commutator flips once the loop makes connection with the other terminal, it then starts to push directly down. Okay? What the loop relies on is having a little bit of momentum to carry it over. So if it carries it over, what will happen is the force now on that particular arm will be down. So it's up in this orientation, hits the commutator split, and then goes dead for an instant, and then as it carries over, it connects, current goes the other way, and now it starts to push down. Because remember, it wants to do this. And to do this, it's changing direction all the time, okay? Oh, every half cycle. Now, what I'm getting at here is that notice these arrows that describe the force. They are all the same length, okay? So, the magnitude of the force on each side of this loop is always the same, okay? However, this is physics, and vectors can often be broken into components. So how much of this force is responsible for the motion of that loop? Like, where is that force the strongest? Well, look at it. It's going to spin about a pivot, which is in the middle, okay? So it's spinning about this central axis. When it's perfectly horizontal, when this loop is perfectly horizontal, which is what that diagram is telling you, the full measure of the force is acting perpendicular to the wire. That gives you the greatest amount of effect, all right? So it's the strongest push that it gets is when it's in the horizontal orientation, when it's in, based on this model, okay, based on this kind of arrangement of magnets. Now, as it moves, you'll find that this force here is still the same, but how much of this force is actually perpendicular to the wire? Because it's only the force perpendicular to the wire that is actually causing that wire to move. The other force that is not perpendicular to the wire is just basically trying to stretch the wire in some way, but it's not actually responsible for any of its motion. Okay? So if you look at the force vector here, there's got to be some component of it, look, didn't draw that very well, there's got to be a component of it which is running perpendicular to the wire. That is the part that is causing it to move, all right? Now, there's another force which is trying to basically stretch the wire. And there's your little right angle triangle there, all right? So what I'm getting at there is the closer this loop gets to the vertical, the less and less of the force acting on that wire is actually responsible for its motion, all right? So really strong here, weaker and weaker and weaker and weaker until nothing, and then weak but getting stronger and stronger and stronger until it gets perfectly horizontal where 100% of the force is perpendicular to the wire and gives it a nice push, keeps on moving, and then it's weaker and weaker and weaker and weaker until it goes vertical where there's nothing again, all right? So this is the relationship between the force on the wire. This is something that they will often test you on, okay? Do you know the difference between, or the relationship between force and torque, okay? So, the force, although the force stays the same and in the same direction the whole time, less and less of it, depending on the orientation, is actually responsible for the motion of the loop, okay? As I've just explained, all right? So, on your help sheet, I actually ripped off a question. I ripped off a question and turned it into a help sheet point for you because it really illustrates the idea of what's going on. Notice I stole basically that diagram and this diagram from a question that you'll actually see in the notes. All right? So, how can we really illustrate the relationship between the force on the wire and the torque experienced by the wire? First, you've got to know what torque is. Completely have no idea whether torque is actually part of the Year 11 course or not. But what torque is, and you can see it here, you can see it written here, is torque is equal to the force applied to an object multiplied by the distance you are from the pivot point. Okay? So, if I have an arm, okay, I have an arm there with a pivot at one end, and I apply a force to it. Okay, let's say I apply a force to actually, I'll write it like that, that's a bit ugly. If I apply a force to that arm, notice that force I've drawn it perpendicular to its motion, to the arm. There's the pivot here. Now, let's say that this is 2 meters long, and I apply a force of 20 newtons. Okay, then the torque experienced by this arm is force by arm. So 20 times 2. That gives us 40 Newton meters. Okay, because it's just force times, force times, we call it radius. Okay, so 40 Newton meters. Now, I can reduce the torque by moving this force to 1 meter. Now, if this force is no longer acting, but I have moved my 20 Newton force to 1 meter away from the pivot, well, how much torque does this arm actually feel? Well, the new value becomes torque is equal to 20 times 1. Now it's 20 Newton meters, okay? So you can see that by moving the force in and out away from the pivot, the further away from the pivot you move it, the greater torque that you get, which is why you'll sometimes see wrenches or spanners that have really long arms. So you put one end on the bolt, and it seems to have almost been welded in position. And with a nice long arm, all of a sudden the torque that you can actually, the rotational torque that you can apply to that bolt is so great that it just either snaps off completely or just opens up, which is really, really useful. Okay, now, let's say, this is just you understanding what torque is, okay? So the higher the torque, the more, so the more torque, the better rotation you get, the faster, stronger rotation that you get. Now, let's take this and change the diagram in a way that links better to what's going on inside one of these loops, okay? Take the loop, all right? Let's say the loop is going to be spinning, all right? Now, in this orientation, we expect either the force, depending on the field and the current, we're expecting the force to be at basically its maximum, right? Now, if I change the direction or the orientation of the loop, keeping the force the same, now I have to resolve that force into a vector, okay? So what that means is only a component of this force actually acts in the direction that I need it to, all right? So, not that way, okay? Now, you notice that as the loop moves, the component, now I've said this already in my earlier discussion, the component of the force acting perpendicular way gets less and less, as I mentioned, all right? So what I need you to do is have a look at this set of graphs, okay? Force, notice force remains constant, okay? Because force is just force, it's always up or it's always down. Notice, for this quarter of a turn, the force is in the up direction. For this quarter, it's in the down. For this quarter, it's in the down. And then in this quarter, it's in the up again. All right? So as it moves all the way around, it's got all 4 quarters of its motion. Because obviously quarters are important here. So there's the motion from here to here, from here to here, and then from here to here, and then back again. So it's the motion of the loop in this setup is it's basically best to be thought of in its sort of quarter turn movements. Alright? Now, its maximum torque occurs when it's horizontal. Okay? So as it approaches vertical, that torque drops. And when it hits vertical, it drops to nothing. Okay? Now, the force is in the up direction because it's in the positive half of the graph. Okay? Now, remember, by changing the direction of the current through the loop, we are going to make the force continue to push in the direction that allows the loop to spin. But what we're doing is, and as it now moves away from the vertical, more and more of its component of the force is actually acting on turning the loop. So the torque goes up until it's horizontal again. And once it's horizontal again, it starts to lose it again, okay? The force keeps on flipping so that the wire keeps turning in the same direction. Force magnitude doesn't change, its direction changes, that's it. But the torque, notice, is always in the same direction, okay? So, that is a really important graph, it's a really important idea to keep in mind. The difference between how torque and force act, all in the operation of keeping this little thing spinning the whole time, okay? Alright, now the only way you can really understand that idea is by focusing on a single side of this loop. You don't look at the whole thing. You look at, okay, force, for example, up, if I've run it a particular way through the wire. Force is up, 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 nothing. Now it's down, 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 down. Okay, now it's down, 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 all the way through here. Now it's up, 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 up. Okay, all the way up. All right, you know what I mean? So the force keeps changing direction on this bar here. Okay, and the reason it changes direction every half turn is to keep it moving in the same direction. Torque is always in the same direction. So when you want to go and explain a question, for example, what is the function of or the role of a split ring commutator, this is the way that you explain it. In the electric motor, look at the wording here is really important. Okay, the electric motor, so the split ring commutator, or often just referred to as commutator, its role in the electric motor is to take the current being supplied by a DC direct current power source and change its direction through the loop, often referred to as armature. Sometimes in some questions they'll say armature, they just mean the loop, okay? Every half turn. You don't write both words. You can say loop or you say armature. I mean, it sounds dicky if you say both, all right? Anyway, I just put them there so that you know what they are. All right. This change in direction of current through the loop will generate forces in the loop, or armature, however you chose to go, that maintain torque. So notice it doesn't say that it keeps the force. See, kids will often write keeps the force in the same direction, so it's always turning. It's like, well, no, it doesn't keep the force in the commutator doesn't keep the force in the same direction. The force is in the same direction all the time anyway, right? It's either up or it's down. Commutator doesn't really do anything in that respect. Just every half turn, it flips it, okay? So what I'm getting at here is the change in direction of current through the loop will generate forces in the loop, armature, that maintain torque in the loop that is always in the same direction, allowing the loop or armature to spin freely, okay? That's the point. So over here, you look at that graph, it's not about keeping the force in the same direction all the time. That's not what it does. It's keeping the torque in the same direction. Notice it's always in the positive. It's always in the same direction. Whereas as the force on that particular arm keeps flipping from up to down to keep it going, okay? Like I said, look at a bunch of animations on YouTube. Makes it so much simpler to picture and build your own little model of how it works, okay? Really, really good way to consolidate what you're learning, what you're finding out with your first time. All right. Okay, we may be very close to the end, I think, which is really good. Let's see, is there any other information here that I have not covered? Okay. No, more diagrams, how the commutator works, I've just gone through that at great length. How real motors work. It's good to look at some diagrams and some video on how a real motor looks and what it looks like. Notice that in a real motor, the commutator, rather than the commutator being a ring, this is why you think to yourself when you look at these questions and these models, oh, you know, if I switch, if I orientate this loop perfectly vertical, where it is not connected to anything, basically, what's going to happen when I switch the current on? Well, nothing. Even if I did happen to just connect one side to one terminal and the other one to the other, and still switch it on, I'm probably not going to get anything more than a tiny little wobble, and it'll just stop, okay? Eventually it'll just stop in the middle, all right, if I do that. So what am I going to do? Okay, so if I do it in that direction, what's going to happen? Well, what is the direction of the force on the top? Well, it might be up, depending on the field and the direction of the current. So on the other side, it's going to be down. So what's happening to the loop in this direction? That's being stretched. That's it. None of the force is dedicated to actually turning the loop, okay? So in this model, it's kind of important that the loop starts here, okay? And yet I know what you're thinking right now. You're like, if I turn on like my blender, you know, I'm making myself a smoothie, okay? There's no point where the blender just doesn't switch on because it happened to, last time you used it, it happened to finish there. And you think, oh, well, now it's not gonna work. I'm gonna have to get in there and push it over. No, it's not, obviously not how that works. What they've done is, like, one way of dealing with that is having multiple loops, okay? Multiple loops that all crisscross each other. They're all insulated from each other. And a commutator that has brakes in it all the way along. So at no point is there zero force on the armature, okay? So wherever you switch it on, it's always going to have some orientation that allows it to move, all right? So there's lots of clever ways. That's all just engineering. Like I said at the start, this is just about how does it work. The engineering is actually way cooler than what you've got here. And even then, it's still even more complex, can be more complex than that. Because in the end, once they've figured out a theory, a way for a principle that works, what happens is then all the other mathematicians and smart people get together and start to figure out, oh, okay, how can we make this really good? And so, okay, so this was all the discussion on torque. You can read all of that yourself as well in addition to what I've got here, what you see in this video. Now we've got questions.